Electric generators work on the principle of electromagnetic induction. This device that I have here is specifically made to demonstrate electromagnetic induction. These are solenoids or coils of wire, and this is an ammeter. I have a bar magnet, and if I take one, say the north pole of this bar magnet, and I push it inside that coil of wire, hopefully you can see the deflection of the needle to the left. When I take that magnetic field out, or take the magnet out, remove the magnetic field, the compass needle deflects the opposite direction. If I take the south pole, I should see a deflection to the right, which I do. And when I move that magnet out, I see a deflection to the left. So north pole gave us a deflection to the left initially, and to the right when I removed it. And so just like a current carrying wire in a magnetic field experiences a force, a changing magnetic field inside a coil of wire produces force on the charged particles in that wire, and therefore produces an electric current. So this would be an alternating current. This is what we have in our plugs at home. It would go a lot faster than what you see here, but the direction of the current rapidly changes in alternating current. So this is electromagnetic induction. And in a generator, you may have seen one of these flashlights before, and if you look closely, you can see that there's a coil of wire in there, and then this little piece of metal here is a magnet, and when you shake it, the magnet passes through that coil of wire and generates electricity, and that is what powers our flashlight. It isn't quite working. But this is a simple generator. So yesterday, I talked with you about electric motors, and I said motors and generators are basically the same thing. It's just the direction that the energy is flowing. So in a generator, we have a changing magnetic field inside a coil of wire that induces an electric current. In our motor, we had a current carrying coil of wire. So we had moving charges inside the wire, and those moving charges were within a magnetic field, and that caused the armature or the coil of wire to turn. So what you see on the screen is a simple electric motor that I just made. So I took a piece of copper wire that has red varnish on it, which acts as an insulator. I fashioned it into a coil of wire, and I wrapped it so that there are two ends that protrude out from that circle. And I sanded these wires, but I didn't sand them all the way around. So you can probably see there that the red varnish is still on part of the wire, and there's the shiny copper. And that's the part where I sanded the varnish off. So it's necessary to sand the varnish off so that current can flow through the wire. But it's also important not to sand all the varnish off, and I can get to that in a moment. What you see on my Elmo, this is just a battery holder, and I took two paper clips and bent them so that they could hold this armature. And I have a couple of magnets there. And so when I set this armature on these supports, current flows through the wire. And I just want to, and now I have a current carrying wire in a magnetic field, and it produces a force on that wire and causes that armature to spin. Kind of messed up my supports a little bit. And so that is a simple electric motor. It takes electrical energy and converts it to mechanical energy. So that spinning coil of wire is the mechanical energy. So I mentioned that I didn't sand the wire all the way around. And the reason that I didn't do that was so that this armature would make complete loops. So it would spin in one direction continuously. If I sanded all the varnish off of the wire, what would happen is this armature would just flip back and forth. And so we could use the right hand rule to think about that. So if the current is flowing through the wire so that on the bottom it's directed to the left, point my thumb in the direction of current. The north pole of this magnet is up. I would see a force on this coil in that direction. Remember, when the coil of wire was horizontal in our motor, we saw minimum torque because the forces were either in, so both forces in toward the center of the circle, or both forces on each, the force on each section of wire, top and side, and the other side would be directed either out or in, so we saw minimum torque. So in this position, there is no potential for it to rotate. If when we bring the top of this wire, so the current now would flow again to the left, it would push the top away. So I would see the bottom get pushed away, the top get pushed away, the bottom get pushed away, the top get pushed away, and it would just flip-flop back and forth. So what I did is I just left some of the varnish on so that the current would be cut, and or the current couldn't flow through the wire, and the momentum could carry my armature around and it could continue to spin in one direction. So that's also known as a split ring commutator.